Hello everyone, welcome to the 14th episode of the series. In this video, we'll talk about cofactors. So far, we have learned about determinant and some of its basic properties. We've also learned an approach where we use row operations to calculate the determinant of a given matrix. And for small matrices, we had formulas to do so. For a 2 by 2 matrix, we know that the determinant is just AD minus BC. And for a 3 by 3 matrix, we can simply use Saris rule and it makes the process a lot easier. So we're going to learn one more method to calculate determinants, and we're going to use something called cofactors. So for a given square matrix A, its ijth cofactor is -1 to the I plus j times the determinant of the matrix obtained by deleting the ith row and the jth column of A. So for example, if we have this 3 by 3 matrix, its 2 comma 1 cofactor is given by -1 raised to the 2 plus 1 times the determinant of 2389, because 2389 is what we get when we delete the second row and the first column. So the position 2 comma 1 is where the entry 4 sits. So if we are computing the cofactor corresponding to that position, we delete the row which houses the 2 1 entry and the column that houses the 2 1 entry. So this cofactor is -1 raised to 2 2 plus 1 times the determinant of this 2 by 2 matrix. We know how to compute this very easily, and we get that this cofactor is 6. So how do we remember the sign of the cofactor? We start with a plus in the first entry of the matrix, so in the upper left corner, and after that, it just alternates in a checkerboard pattern. Okay, so let's look at an exercise. So we're given a 4 by 4 matrix, and we want to compute the cofactor at position 3 comma 2. So that's the intersection of the third row and the second column, and these are the row and the column respectively that we are going to delete. And because it's at position 3 comma 2, it's going to be a minus sign. So C32 can be computed as -1 raised to 3 plus 2 times the determinant of the 3 by 3 matrix that we get by eliminating the third row and the second column. So it's the determinant of the matrix given by 2 1 1 0 -1 3 1 2 5. So the 3 by 3 determinant can be computed by converting it into the determinant of an upper triangular matrix while we keep track of the changes. So I'm not going to go into the details here, but you can use the rule of Saris, or you can convert it into an upper triangular matrix like this one, and eventually you will get to a point where you'll see that the determinant is 18. So this 18 is the determinant of the original 4 by 4 matrix. So now that we know how to compute cofactors, we're going to use that to compute the determinant of a square matrix. So if A is an n by n matrix, the cofactor expansion of the determinant of A along the ith row is given by this formula. So what's happening here is if your cofactor expansion is along the ith row, we're going to start from the first column and we're going to move along the ith row, and at each step we're going to multiply the entry in the ith row with the cofactor corresponding to that position, and we keep moving along ith row. We do it for each entry in that row, and then we take the sum. So this is what we mean by the cofactor expansion along the ith row of the determinant of the matrix A. So let's look at an example. So we're given our very familiar matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the cofactor expansion along the first row is going to look like this. So we're going to start from left-hand side, and we're going to travel along the first row. So we have 1 times the cofactor corresponding to 1, 1. So to compute the cofactor corresponding to 1, 1, we eliminate the first row and the first column, and therefore we are left with 5, 6, 8, 9. And we know how to compute this determinant. It's 5 times 9 minus 6 times 8, and that's just minus 3. So we get 1 times the determinant of 5, 6, 8, 9 plus 2 times minus determinant of 4, 6, 7, 9 plus 3 times the determinant of 4, 5, 7, 8. We compute all of these smaller determinants individually, and we solve it, and we get to the determinant, and that's just 0. We can also compute the cofactor expansion along a different row, and we're going to see that we get the same determinant no matter what. So intuitively, we travel along the ith row, and we take the alternating sum of each entry times the determinant of the complement. And by complement, I mean the remaining part of the matrix that we get upon deleting the appropriate row and column. So since the determinant of a matrix is the same as the determinant of its transpose, we can also use columns instead of rows. So we can define the cofactor expansion of the determinant of a matrix along the jth column. So the idea is very similar. So instead of moving along the ith row, we move along the jth column, and at each step we multiply the entry with the cofactor corresponding to that position. So for example, in the same matrix that we saw a moment ago, we can use cofactor expansion along the second column. So we're going to get 2 times the 2 times the determinant of 4, 6, 7, 9 times minus 1, because if you remember the checkerboard diagram, there's a minus in the position 1, 2. So we're going to get 2 times minus determinant of 4, 6, 7, 9 plus 5 times the determinant of 1, 3, 7, 9 plus 8 times the determinant of 1, 3, 4, 6 times minus 1. You simplify this, and you again get that it's 0. Okay, so let's look at an exercise. We're given a 4 by 4 matrix, and we want to compute its determinant using cofactor expansion. So the easiest thing we can do is cofactor expansion along column 3, because all the entries are 0 there. So every single product in the sum in the cofactor expansion along column 3 would be 0, and therefore determinant of A is 0 as well. So this brings us to a fact that if A is an n by n matrix with a row or column of zeros, then its determinant has to be 0. Let's look at another exercise. So we want to compute the determinant of this 5 by 5 matrix. So now if we have to use cofactor expansion, we have to make a choice, and the choice is about which row or column do we want to use for the expansion. So we're going to use row 4 because it has 5 entries and 4 of them are 0. So the sum is going to be very simple. So using cofactor expansion along row 4, we get A43 times C43, because all other terms in that sum are 0. So we just get minus 1 times the determinant of this 4 by 4 matrix that we get upon deleting the fourth row and the third column. And then the 4 by 4 determinant can be computed by cofactor expansion along the new third column, because um, like there are 4 entries in this column and 3 of them are 0. So the determinant is going to be very simple again. So we get 2 times this 3 by 3 matrix, and this 3 by 3 matrix can be computed using row operations or rule of Saros, and you can check that it's actually equal to 4, and therefore the determinant of A is -1 times 2 times 4, and therefore is equal to -8. So when should we use cofactor expansion? When there are a lot of zeros in a in a fixed row or column, because that's where we actually take advantage of cofactor expansion. And like this also becomes the weakness of this method, because without tricks like these, this is much slower than using row operations. So it's also important to note that cofactors can be used to compute matrix inverses. So if A is an n by n matrix with non-zero determinant, then it's invertible, and the inverse of A is given by 1 over determinant of A times the matrix given by the cofactors. So you have to be a little careful, that because the ijth entry in this matrix is actually the j comma I cofactor of A, and of course A divided by the determinant. So please be careful. So note that if you were to write a code for computing the inverse of a matrix, you would not use this formula, because it's very, very inefficient, because you would need to compute the determinant of the matrix, and then you would also need to compute n squared cofactors as well. And there are more efficient ways to compute inverses on a computer. So I want to finish this episode by a small exercise. So we're going to use cofactors to recreate the formula for A inverse if A is a 2 by 2 matrix. So because this is a small matrix, we only need to compute 4 cofactors, and even the computation is not hard. For example, if we want to compute 311, we remove the first row and the first column, and that just leaves us with a 1 by 1 matrix with entry D, whose determinant is just D, and therefore C11 is just -1 to the 1 plus 1 times D. So similarly, we get the other 3 cofactors. We're going to get -C, -B, and A, and then we just use the inverse formula. So we get 1 over determinant of A times the matrix given by cofactors, and because the determinant of A is just AD minus BC, we get the formula that we all know and love. So with this, I would like to end this episode. In this episode, we learned about cofactors, and we learned how to use them to compute determinants and inverses. I will see you guys soon. Up until then, happy learning.